In the last video, we talked about heat in the atmosphere. Today, we're looking at how the atmosphere moves. I'll be honest, this is where things get complicated, so buckle in, cause it's nerd time! Last time, we learned that the atmosphere is constantly moving because Earth is unevenly heated by the sun. Warm air rises, cool air sinks, and pressure differences drive motion. If Earth didn't rotate, Earth's circulation would be relatively simple. Instead, Earth's rotation reshapes atmospheric motion into organized, persistent patterns. In the simplest possible model, warm air would rise at the equator, flow to the poles at high altitude, cool, sink, then return along the surface. This single-cell circulation would efficiently redistribute heat from equator to pole. However, this model does not match reality. Earth is too large, rotates too quickly, and loses heat too unevenly for single-cell circulation to remain stable. Instead of one global loop, atmospheric circulation organizes into 3 primary cells per hemisphere. These cells form because rising and sinking air can't maintain a straight path over long distances on a rotating planet. As air moves away from the equator, it cools, becomes denser, and eventually sinks, creating zones of persistent high pressure. These rising and sinking regions divide the atmosphere into preferred circulation patterns. The Hadley cell dominates tropical circulation. Near the equator, intense solar heating causes warm, moist air to rise, creating a zone of low pressure. As this air rises and cools, it spreads poleward aloft, loses energy, and sinks around 30 degrees latitude. This sinking air creates subtropical high-pressure belt regions associated with dry climates and deserts. At the surface, the air flows back toward the equator, completing the loop. Poleward of the Hadley cell lies the ferrocell, which is driven indirectly by the motion of surrounding cells rather than direct heating. Air within the ferrocell moves poleward at the surface and equatorward aloft, producing variable and often unstable weather. Near the poles, the polar cell forms as cold dense air sinks and spreads equatorward along the surface, rising again at higher latitudes. Together, these 3 cells form the basic framework of global atmospheric circulation. As air moves across Earth's surface, its path appears to curve due to Earth's rotation. This apparent deflection is known as the Coriolis effect. In the northern hemisphere, moving air is deflected to the right. In the southern hemisphere, it's deflected to the left. The Coriolis effect doesn't create motion, it just modifies motion that already exists. Its strength increases with latitude and becomes negligible near the equator. The interaction between pressure gradients and the Coriolis effect produce persistent wind belts. Surface winds flowing toward the equator become the trade winds. Mid-latitude surface winds become the westerlies, and near the poles, surface winds form the polar easterlies. These wind belts influence ocean currents, climate zones, and long-term weather patterns. Global circulation is fundamentally a heat transport system. Excess energy from the tropics is redistributed toward higher latitudes through atmospheric motion. This process moderates global temperature extremes and shapes Earth's climate. In short, without atmospheric circulation, the equator would be far hotter and the poles far colder. To bring it all home, uneven heating creates pressure differences create motion, Earth's rotation organizes that motion, and the result is a planet-scale circulation system that governs weather, climate, and life at the surface. In the next lesson, we'll bring back water into the picture and examine how moisture and latent heat interact with this global structure. Stay nerdy!